Welcome to the final project presentation of course Engineering 990B. The topic of our project is optimization of in-motion wireless charging system of electric vehicles and its future prospects. In the beginning, I want to give a special thanks to our project supervisor, Dr. Ashraf Ali Khan, and our project coordinator, Dr. Mohsin Jamil. We are a group of three. Myself, Shubhashish Rai. I did the part of system design and MATLAB simulation. Pashukumar Das did economic analysis and Home Pro simulation. And Abhijit Bishas completed the battery management and battery efficiency analysis. To talk about the agenda, we have introduction, rationale, system design, economic and environmental analysis. Further, we have battery management system, result and discussions, and at last conclusion. To introduce the project, the Dynamic Wireless Charging System (DWCS) charge sustaining in motion charging of EV. So our target is to charge the EV while the EV is in motion, reducing idle time and extending driving range. It will obviously have the effect to reduce the charging time because we'll charge the vehicle on motion. Significant greenhouse gas emissions from ICE century-old technique. Environmentally friendly transportation, battery technology and cost of efficient battery materials, static and dynamic charging wireless systems, lack of research on economic analysis of DWCS. So that's a pretty new idea. So this work will help the next level researchers to further develop the research. So this is our rationale. That means our target of the project. So obviously our first target is to increase the EV driving range, and next our target is the increasing battery charging efficiency and reducing charging time. We will also analyze the economic benefits and analyze the environmental benefits, and lastly we'll talk about the battery management system. So this is our system. We will design the systems in a way that the transmitting coil will be mounted on the road and the receiving coil will be placed in the vehicle, and we will place a series of coils in the roadway, and the car will take the charge while in motion. So in the system we will take the power from the grid and convert it to DC. Then to make the wireless power transfer, we will again convert the DC power to AC and make the power transfer. And after receiving the power in the vehicle, we will again convert it to DC to charge the battery. This is our circuit diagram. We use the DC supply which will be given in the road, and in the roadway there will be coils, and we used an inverter to convert this DC supply to a high frequency AC supply, because we will need the AC power to make the power transfer or wireless power transfer possible. In the inverter side, we used a pulse generator, high frequency pulse generator, uh, to to create a AC supply of high frequency. And after receiving the power in the vehicle side, we used a rectifier to convert the AC power into DC power. And lastly, we used a filter to filter out any kind of ripple in our DC, and we will charge the lithium ion battery bank. We simulated the system in the MATLAB environment or simulating environment. This is our system model. We here in the right side there are some system parameters. We use the DC input voltage of 500 volt. The inverter frequency is 10 kilohertz, and the copper coil specification is given here, the length, width, and the cross section of the coils. And the battery parameters is all given in table 2. The battery type we used lithium ion. The battery bank voltage is 400 volt, which is typical for the EV, and the rated capacity of the battery is 100 ampere hour. The kilowatt rating is 40 kilowatt. We consider the initial state of charge is 25%. This is our simulation output. The first figure shows the inverter output voltage and current at 10 kilohertz. Here we see the voltage and current wave shapes. They are in phase. The second one is rectified output DC voltage and current. We see the nice DC voltage and current in the output. And the third curve is the voltage and current received and secondary coil. Here are some continuation of the simulation results. The first curve shows the state of charge increase of the EV battery in standstill condition. Here we can see that there is almost a 0.0012% charge is accumulated in zero point 0.1 second, and the battery voltage is increased with the state of charge. The battery current, the charging current is between minus 40 ampere to minus 50 ampere, which is shown in the third figure. And the transmitted and received power we are looking in the figure 4. So while the vehicle is in moving condition, the state of charge, battery voltage, battery current, and the received and transmitted power is given here. Here we see almost see the same identical results as the as the stationary condition. And we also simulated the system in 5 kilohertz uh, inverter frequency, and the transmitted and received power is given here. And we also compared the current in standstill and moving condition. This is the summary of the simulation result. Here I can see the state of charge increased in is 0.00117% in zero point 0.1 second, and in moving condition is almost the same. Battery charging current is slightly lower in the moving condition, and battery voltage increase is almost the same. And the most notable is the efficiency, which is in moving condition, the efficiency slightly decreased almost by 1.5% to 2%. From the simulated graph of transmitter and receive power at 5 kilohertz inverter frequency, we can calculate the efficiency, which is found to be 93.33%. So by increasing the system frequency and choosing the compensating capacitor accordingly, we can achieve increased power transfer efficiency. Now I'm handing the slide to Pashukumar Das.
Thank you, Mr. Shubhashish Roy, for giving me the floor. So, in this section, I'm going to talk about the economic analysis. In this section, we have considered two different economic evaluation. So, in the first category, what we did, we have considered a charging lane. So, the charging length we consider is 1 kilometer, and we have considered zero point 0.5 meter for each coil length, and there is a distance between these two coils which is zero point 0.5 meters. So that means in this 1 kilometer length we have around 1,000 copper coil transmitting the power to the vehicles. So for this 1,000 coil, we have calculated in each coil it takes around 17.2 kg of copper. And if we consider the price of the copper, which is 15.6 CAD approximately, the altogether for all the coppers, uh, the cost is for the per coil is 348 CAD approximately. So if we consider for 1,000 copper coils, the total cost is 347,000 Canadian dollar. And we have done one more thing. We considered 30-second duration stop time in each of the intersection, and within this 30-second duration, electric vehicle can get 0.348% charge. So if we consider 75 stops in a day during their driving, it can charge 25% of the total capacity. By saying that, we can explain that we can reduce 25% of the battery capacity from our original consideration. So the our original consideration was 40 kilowatt hour for each car. Now we're gonna reduce it to 30 kilowatt hour. If we reduce this 30 kilowatt hour, there is a huge benefit, economical benefit, that can be saved from the battery sections. So the savings from the battery capacity reduction is around 397,000 Canadian dollar. That means overall we are saving 48,000 dollar for a sample calculation in this economic section. In the next economic model, what we have considered, like electric vehicles are developed, and invention is related to the uh, environmental goal, economic goal, and energy related challenges. So to fulfill this criteria, the we have considered on-site generated solar power into the conventional grid supplied electricity. That's why we used Homer Pro simulation to do this analysis. In these sections, we have considered 50% of the load of its total capacity during the daytime, so that we can generate the solar power and we can supply this solar power to the grid. So in this simulation model, as we are seeing, we have as we see, we have conventional grid with the AC bus. I have PV panel for the solar generation in the DC bus, and there is a converter that will convert the DC voltage to the AC, and we can use that into the grid. So the maximum capacity that we have considered is 800 kilowatt hour per day. And according to this simulation, the optimum model that we have find is showing that the our capacity for the solar generation is around 800 kilowatt, and the system converter capacity is around 330 kilowatt, and the grid power is connected with this. In the next slide, we are seeing the result of our simulation. In this section, it is evident that capital expenditure incurred for solar and system converter. There was no capital cost for the grid. Initial capital expenditure was for the system related. It was around 155,000 Canadian dollar. However, the operating cost for the grid accounted for 129,000 Canadian dollar. There was no operating cost for the solar panels or the system converter. The replacement cost, we are seeing that around 5,000 Canadian dollar, and the estimated salvage value is around $1,000. So the total net present cost for the economic model, we are seeing it's around $53,000. So in the next slide, we are seeing how the solar panel is producing power throughout its year. But as we mentioned, we have considered the solar panel only for the daytime. That's why it's showing on the graph that it is produced solar power in between 6 a.m. to 6 p.m. And there is a increase in the power generation sector during the summertime, as we have the better solar irradiations during that time, but it has less power generation during the winter time. In the next slide, we are seeing that uh, the total energy purchased from the grid and the total energy sold to the grid, and what is our net spending on this. So throughout the year, if we see the total, we have purchased 143,000 kilowatt hour, and the percentage of energy purchasing is reduced from the month of May until the month of September, because during this month the solar production is more, and that's why we purchase less. And at the same time, we sell more power to the grid as we have generated more power than our required capacity. So at the end of the day, we are seeing that we purchased 143,000 kilowatt hour and we sold 544,000 kilowatt hour to the grid. So the best economic model that we find is here, the net present cost for the base model. Here we need to mention that the base model means the grid power, so the net present cost for the grid power is above 452,000 dollar. For the economic model, it is showing that the $53,000 only. There is no capital expenditure for the base model as it is already conventional model and it is connected. So for the economic model, we have mostly spending on solar panel and the system converter. There are some operation expenses basically for the grid, and we see there is a huge gap between levelized cost of energy per kilowatt of hour compared to the grid and the economic model that we are suggesting. But the most important thing, the goal of this electric vehicle is the environmental pollution. So we see that there is a more than 50% reduction of carbon dioxide emission from base model to the economic model. In this section, we are seeing that this is the cumulative cash flow. In this cumulative cash flow, uh, it signifies the time value of money. That means the sum of the discounted cash flow over the entire project lifetime. In this simulation, base model was considered grid power. And after comparing economics, it was found that the economic model internal rate of return is 27, more than 27%. That means the project is likely to be financially successful, and the discounted cashback period is 4.16 years. The simple payback period is 3.6 years. So it is a huge achievement, we think, from this simulation that we have found. And on the next graph, we see that the renewable energy penetration level, as we have said that what we produce, we use less. So we sold more uh, power to the grid. That's why our renewable penetration is more than 100% here. There are other some economic benefit of in motion wireless charging vehicles. So this is increased driving range and efficiency. One of the primary drawbacks of conventional electrical vehicle is their limited driving range and requirement for the frequent stops to recharge. So it will eliminate. It will enhance the energy efficiency. That means the energy transfer efficiency can be optimized while designing the in motion charging system. This means less energy is wasted during the charging process. It will reduce the pressure on the grid. That means continuous charging made possible by in motion wireless charging can help distribute the day's electricity demand more evenly. It has some potential to generate the revenue, and it will support for heavy duty vehicles, and it can serve the long range distance. There are some environmental benefit of this project, and we are trying to dig out that. In these sections, we have first improved air quality. As we all know that the conventional internal combustion engine uh, emit carbon dioxide gases to the environment. So these will actually create some improved air quality for our environment. It will have less noise pollution compared to the cars with internal combustion engines. It is quieter, and it has natural resource preservations. That means electric vehicles use no petrol or diesel and have fewer moving components, which lowers the demand for fossil fuels. We may reduce our reliance on limited fossil fuel supplies and encourage the use of cleaner and sustainable energy. And the last one is integration of renewable energy sources. As we have said, we can produce power from the solar or from the wind, and we can use that power to charge the electric vehicle. That will actually help us to achieve renewable energy goals in the future. So this is all about my presentation. The next part will be covered my co-authors, Mr. Abhijit Bishesh.
Thank you, Pasha Kumar, for giving me the floor. So in this part, I would like to discuss the battery, means the heart of electric vehicles. So I know that we all know that the importance of battery, the convenience of fast charging is become a reality for EV owners. New battery technology and charging infrastructures developments are making it possible to recharge EV quickly. Furthermore, advancement in battery management systems are increasing battery lifespan, reducing concerns about the degradations over time. So to be good, to get some good output from battery management system is very much necessary. So here we see that there are several uh, sectors for battery management systems. Like the battery should be designed, a mechanical design means the battery should be designed perfectly for that particular EV cars. As you see that we know that with time being different types of EVs in the market in these days, and since the last 10 years the revolution or evolution is so massive and it's been changing continuously. So designing of a battery, a perfect battery, it's very important. It should be accurate state of charge or state of health. It should have some protective measures for the car because it's very important. It should have some thermal managing, the means we should design battery, we should use such elements for the battery, or we should pick a perfect chemical for the battery that make it so thermal efficient, thermally safe. The charge and discharge control, the right cells, it's a very important thing because till these days, means since last years also, the lithium ion battery or manganese battery is widely used, but with time being recently we will different automotive companies have introduced solid state batteries in market. So we should know, we have to know the right cells for the right EV cars and increase lifetime. So in our next slides, I would like to draw some importance of battery management system. Like it's guaranteeing the safety and reliability of the battery, monitoring the assessing battery condition, managing the state of charge effectively, ensuring cell balance and controlling the operating temperature. Means we have to balance the cell. We have to design the battery pack in such a way that that battery pack is very much thermal efficient. It's very much thermal efficient, and then efficiently handling regenerative energy, and it allows for monitoring the entire battery pack's charge rate down to the level of individual cells. It undertakes specific activities against overheating and thermal imbalance to ensure the safety and reliability of electric cars. Basically, what we know that for a battery management system, we have to design the battery. We have to pick the proper elements, proper liquids, or proper materials for the battery for our desired electric vehicles to make it more efficient and make it more convenient for the customer, for the users. Next, the battery algorithm means where we can see that standard method for calculating state of charge. Where in the first part we see there is a battery pack. So basically here we put two cells, but in these days we'll get so many cars who has a large battery pack, and the battery pack is connected with the measurement. Means we have to, what we have to measure, we have to measure its thermal capacity, its current, its voltage, everything. So here you see that a battery pack is connected with the measurement, and from that measurement data is supplied to the cell balancing. Means like if the battery pack is heated, then cell balance pass the data to the charge and discharge condition, and then our battery pack is controlled. A standard method for calculating state of charge is direct measurement involving the evaluation of open circuit voltage and inferring state of charge from pre-stored discharge characteristics. However, this technique does not account for temperature's impact on SOC. Therefore, it becomes essential to employ a methodology that considers these effects perfectly. So, the solid-state battery is a new hype in the world of electric vehicles these days. As I said earlier, and the Toyota, as you say, the Toyota is the pioneer to introduce solid-state battery in market, and there is a car that is developed by Toyota that can run 786 miles in just 10 minutes of charging. So yeah, as I said that early, still we are using those conventional lithium-ion battery, that manganese battery, that cobalt batteries, but they all have some limitations. It's mostly, though they are high energy density, they are good. They have good charging performance. Most common EV models, but at the same time, their life cycle is very short. They have high thermal runaway issue, and they are very much unsustainable and expensive materials. On the other hand, the solid state battery promises quick recharging and discharging, longer life cycles. A constable battery, better energy density, lower cost, and improved safety. In this, a solid replace means the difference between the solid state battery and the other lithium ion batteries means the electrolyte. In other batteries, they use a liquid electrolyte that make it more less efficient, but in solid state battery, they're using solid electrolyte to increase its energy storage capacity. The solid state battery develops by quantum space for EV can go nearly 400 miles on a single charge and can charge for 0% to 80% less than 15 minutes. And other pioneer EV industries, they are working on it, and we hope in next year we're gonna get a new vehicles that introduce these solid state batteries in their device in their cars. So working principles of SSP that I already mentioned that, whereas the other lithium-ion batteries, the cathode and anode is separated by a liquid electrolyte, while in the SSB it is component of solid. There is solid state electrolyte that act as a separator sandwiched in between to keep things apart. Typically, it is a thin plastic film. It served as a ions conduct with simultaneously acting as a mechanical separator between the anode and cathode and as an electrical insulator. So this is very safe and secure. And the advantage of solid state batteries, its energy density, its rapid charging, its high stability, rapid construction, store more energy but no anode because it's a solid state electrolyte, compact and lightweight, safety matters, a complete off-grid experience, simple and streamlined manufacturing process. And to reach our conclusions, we have just figured out that within the scope of this project, a wireless in-motion electric vehicles battery charging system was successfully implemented that has almost identical performance in both standstill and moving conditions. Because still we have the batteries, we have the vehicles, electric vehicles who can what can be charged in the standstill conditions, but it's a world of race. Everything is moving faster every day, and in near future the race will be more tight. So we have to develop some strategy, we have to develop some technology that can be used to charge our in motion vehicles. And so the project also includes a comprehensive financial analysis of the in motion charging systems, revealing promising prospects for substantial saving in terms of EV battery capacity. Furthermore, the integration of solar energy with grid power during daytime operations has the potential to significantly reduce the levelized cost of energy per unit of electricity generations. And here we have some recommendations for further study, like improvement of safety of vehicles and passengers, because improve safety is always an issue, and we have to work on it. The because as it's an electric device and we are using battery, so safety is a very important issue. Developing the billing system and further economic analysis and feasibility study to make it more possible so that any country, any developing or developed country can implement this in their busy streets. So this is what all about our presentations on these topics, and yeah, we are would like to thank our would like to pay our thanks to our project coordinator Ashraf Ali Khan and our honorable project coordinator Mohsin Jamil for their entire guideline throughout the projects. And thank you everyone for listening us.